Okay, practice D. We're going to do number 1. And this is electric field strength. And we're going to apply the same laws of superposition that we used before, because the electric field is a vector quantity and it has both magnitude and direction. So it says a charge Q1, so we're going to write our given, is 5 microcoulombs. Now before I do anything else, micro is a prefix. I'm going to need to know this prefix for the test, and micro is 5, so micro is 10 to the negative 6, so that's Q1. It's at the origin, so now already I know. Before I even go on, remember we want to chunk problems. So before I go on, telling me that it's at the origin is important, so I'm going to draw myself a picture. This is my Y, this is my X. And Q1 is at the origin. And it's positive, so I'm just putting that there because the sign of the charges is important when I'm looking at the direction of the electric field. A second charge, Q2, is equal to negative 3 microcoulombs. So that's negative 3 times 10 to the negative 6 coulombs, and it's on the x-axis at 0.8 meters. So now I'm going to draw that over here. This is Q2, and I know that this distance from here to here is equal to 0.8 meters. Find the electric field, so I want to find E. At a point on the y-axis, 0.5 meters from the origin. So up here, and I'll call this point P, I want to find the electric field strength. And I know that this distance is equal to 0.5 meters. Now, I didn't give myself enough space. First of all, I'm going to look at Q1. Which way, before I do any calculations, which way does an electric field act out of a positive charge? The electric field lines act outward, away, right? So I'm going to draw this away from Q1. This is E1, and I'm going to draw it up here. So I kind of ran out of space. So that's E1. So Q1 to this point charge, it acts out of the positive. So it's going to go this way. Now, when I'm looking at the electric field that exists between these two, the electric field for this one always is going to go into the negative. Remember, it's out of positive and into the negative, so it's going to go like this. So this is E2. Now I have my direction. Okay, all I'm going to do is I am going to find this E1, I'm going to find this E2. Once I find each one, I can find, this one only has a Y component, this one has an X and a Y. I add them up, I find the net EX, the net EY, and I do, again, superposition just like I did before, but now we're doing it with E. Where do I start? Well, first I start with the electric field strength, okay? So the equation is E1 is equal to K Q1 over R1 squared. So this is the distance between this charge and this point P. So that's equal to 9 times 10 to the 9 Newton meter squared per Coulomb squared times Q1, which is 5 times 10 to the negative 6 coulombs, divided by the distance between them. So this is going to be 0.5 meters squared. So now in my calculator, I'm going to do that. So I always start here and go backwards. So 5, I'll put it up, 5 EE, so then I can see it's an exponent, to the negative 6, so I see 5 times 10 to the negative 6, times 9 EE9 equals, divided by 0.5 squared equals, and my answer comes out to be 1.8 times 10 to the 5, and my unit is a Newton per Coulomb. Now, if I want, I can carry my units through and cancel them to check my work, but in this case, remember I have a Newton meter squared per Coulomb squared times a Coulomb divided by a meter squared. So this cancels with that, this cancels with one of those, and I end up with a Newton per Coulomb, which is my correct unit for electric field strength. Okay, now I'm going to calculate E2. So E2 is equal to K Q2 over R2 squared. So that's equal to 9 times 10 to the 9 Newton meter squared per Coulomb squared times negative 3 times 10 to the negative 6 coulombs divided by the distance between them. Wait a second, let me look at my picture. Do I know what this distance is? No. I know this distance and I know this distance. This is a right triangle. So in order to find this distance here, which is the hypotenuse of the right triangle, I can use the Pythagorean theorem. Now, we used the Pythagorean theorem so long ago, I don't have to calculate it separate. I'll just put down here, this is equal to the square root of 0.5 squared plus 0.8 squared. Now, I might want to calculate that separately here. Like, I might want to do the numerator and then the denominator, because to do all this, you might make a mistake in your calculator. So I might want to do it in 2 steps and say 0.5 squared plus 0.8 squared equals square root, and then say my denominator is one number, and then my numerator, 3. So here, So anyway, if we do this on the calculator, you have to be sometimes careful with your significant figures. You get negative 2.9 times 10 to the 4. And that's newtons per coulomb. Okay. Now, what do we do next? This is where we're going to make our chart. So in our chart, we're going to have E for the electric field strength, and we're going to have the X, and we're going to have the Y. So now we're going to have E1, we're going to have E2, and then we're going to have E total or net. So when we look at it, first let's look at E1. E1 goes straight up. E1 goes straight up. So does E1 have an X component? No, it's all a Y component. So now in my chart, this is 0, and this is positive 1.8 times 10 to the 5 newtons per coulomb. Over here, I like to draw things to the side. So remember, E1 went up like this, so that one's all Y. Now E2 looks like this. There's E2. And remember, I need to find the components from where I start to where I end up. This is going to be E2Y, and this is going to be E2X. Remember, that's vector resolution. Now, I can do it any way I want. If I want, I can find this angle here, theta, using the sides of the triangle. Like, I know that the similar triangle, this was 0.5 and this was 0.8. Therefore, I can find this angle. So I could use sine and say sine of theta if I wanted to is equal to, oh, not sine. I could use tangent and say it's opposite over adjacent. So tan of theta is equal to 0.8 over 0.5 . Okay, so when we figure out this angle comes out to be 32 degrees. All right. So now I want to find E2x and E2y. So E2x is equal to E2 cosine of 32, and E2y is equal to E2 sine of 32. So now when I put this in my calculator, remember E2 I already know, this is E2. So I put that in my calculator. And E2x comes out to be 2.5 times 10 to the 4 newtons per coulomb. And E2y comes out to be 1.54 times 10 to the 4. Now, the most important thing in this chart is the signs. What direction are they pointing? So what I need to do is I need to look at my vector diagram. E2y points down, so that one's going to be negative. And E2x goes to the right, which is going to be positive. Remember, we're still using our standard Cartesian sign convention that up and to the right is positive from our frame of reference. So remember, here's our frame of reference. We're using the same sign convention, and that is extremely important here because when I add my vectors, I need to know the signs. So now I'm going to add these up. That's easy, 2.6 times 10 to the 4. And then when I add these up, 1.8 this comes out to be positive 1.65 times 10 to the 5 newtons per coulomb. So we're almost done. Now I have my x component. This is EX. I have my y component, and I just want to find my E, my net electric force. So what I'm going to do is, the signs of these are important. So what I'm going to do is, first, here's E, the total E here. This is EX. From the head of this vector, I'm going to do the tail of the other. This is EY. The direction's important. This is positive, so according to my sign convention, right is positive. This is positive. According to my sign convention, up is positive. From where I start to where I end up, this is how I'm going to draw my vector. So this is, I'm going to call it T for total. It's your net. Remember, we're using the standard Cartesian sign convention. Up and to the right is positive. Now this is easy. To find the magnitude, magnitude means how much of this, I'm just going to use the Pythagorean theorem. So that's equal to ETX squared, and I'm just calling it total. If you want to call it net, it doesn't matter. You call it whatever you want. And that's equal to the square root of 2.6 times 10 to the 4 squared plus 1.65 times 10 to the 5 squared. So now on my calculator, 2.6 EE4 squared plus 1.65 EE5 squared equals square root. So it comes out to be 1.67 times 10 to the 5 newtons per coulomb. Am I done? No. I am not done, because we know at this point that all vectors have both magnitude and direction. So we need to find the direction. The easiest way to measure the direction is from the tail of the resultant. And it's going to be easiest to find the angle inside that triangle. Okay? So I have opposite and I have adjacent, so I'll do tangent. So tan of theta is equal to opposite over adjacent. So it's the y over the x. Remember, this is opposite. This is adjacent. So that's going to be 1.65 times 10 to the 5 divided by 2.6 times 10 to the 4, and that's equal to tan theta. So now on my calculator, I'm going to say 1.65 EE5 divided by 2.6 EE4 equals, and that gives me 6.3, but that's the tan. I just want the angle, so I'm going to press second tan. Oops, I think mine's in scientific. So it's 81 degrees. 81 degrees from where? Well, if you look at my picture, this is above, so I would say 81 degrees above the positive x-axis. So this is my final answer. So what we did was we did all the same stuff we did before. First we drew our basic picture. So we drew the electric fields and the direction in which they were acting. Okay? Then we actually calculated the magnitude of each electric field. Okay? Then I found the x and y components of each electric field. I added them all up. I found the net electric field in the x, the net electric field in the y. After I did that, I found the net electric field by adding my two vectors head to tail and finding the resultant, and because vectors had both magnitude and direction, then I use a definition of tangent to find the direction. So that's my final answer. And that's it.